Hi guys, this is Big Data Guy and welcome to Spark tutorial for performance optimization. Objective of this tutorial is to learn about how to write programs that are going to be efficient and performant. And we also want to be able to eliminate any bottlenecks in the programs that we write. So let's get started. So what I want to do is when I talk about a particular measure to improve the performance, I'm going to show you with an example code of what do I mean when we talk about that particular measure, right? So the first measure that I'm going to talk about is reading only the necessary data and required data. So one of the most efficient indicator of Spark program is to be able to process as little data as possible. And the way that you want to be able to do that is to be able to filter the data as early as possible, right? So if you can filter the data right at the source, then you are going to get very high performance compared to the program that does not filter the data at source, right? So over here, we have two different programs. One is program using SQL Server, where Spark is connecting to a Postgres SQL Server and fetching the data and pretty much applying the filter condition immediately, saying that I want to have age greater than 30, right? And once we have read this data, we should also cache this data, which we are going to talk about next time regarding how it improves the performance, right? Similarly, in Parquet file, as you can see that we have selected the columns right in the beginning. And the reason why I have done this is because Parquet, like we covered in the last tutorial, is a columnar storage. You are able to read a particular column and not go through entire data set. So if you have even like terabytes of data, you could save significant amount of bandwidth when you're trying to go and read the data, right? So that's number one. Make sure that you filter at the source and you only read the necessary and required data that you need for your analysis purposes. Second one, extending from the previous slide, is that we want to be able to cache the data frame as early as possible, right? And some of the good checkpoint to cache the data frame is right after the join or right after reading the data frame from Parquet file or SQL Server or anywhere, right? The reason why you want to do this is that Spark is one, lazily evaluated, and second is that it follows the DAG, right? So each time you request for something like show or something, if you have not cached the data frame, then it's going to go all the way back to the source and try to go and follow the execution path in order to get to this location, right? However, if you have cached the data over here, then it's not going to go back to the source. It's just going to, get the data right from over here, right? So you can imagine that, the reason why you cache the data after join is that join is a very expensive operation in Spark, and oftentimes it requires a lot of shuffling of the data across different cluster. Sorry, not different cluster, the different computers within the cluster, right? So that involves a very high network or bandwidth IO that we want to make sure that does not happen again, right? So if you do not cache the data after joining, then what happens is that when Spark goes, if you go and do some additional analysis right after join, and then you say that you want to show the data frame, then it's going to go and perform the join again, right? So the entire idea over here is that once you cache the data, you can go and split this data into two different way to analyze this in two different formats and then eventually combine it, right? But if you do the same thing without caching, then what happens is that it's going to go and perform the join twice for each of the different analysis that you're trying to do, right? So if you are intending to do like 5 or 10 different type of analysis on this filtered data frame or clean data frame that you have created after joining, then what would happen is that it's going to go and redo the join 10 times, which is not going to be efficient, right? So you want to be able to cache the data as soon as possible. And secondly, going back to the reading the data, is that even if you're not cached the data after reading it, then what Spark is going to do is that for all those 10 different analysis paths that you're trying to follow, it's going to go back and read data 10 times for each of those analyses, right? So the best way to utilize cache is right immediately after reading and then filtering the data, right? Once you figure out this is the right amount of data I need, immediately cache the data frame. And then the second best place to cache the data frame is immediately after join operation, right? And you want to make sure that you do not want to overdo the caching, because Spark stores all of its data in memory, and if you keep caching more and more, then you are reducing the amount of memory footprint that your Spark cluster can utilize, right? So there's a trade-off between how much should you cache and versus how much should you go and do the compute, right? Because caching is going to utilize some memory in your cluster, and you want to make sure that you do caching efficiently and at the right time, right? So one good example would be that if you're not going to do any operation after joining, and it's just going to be a simple couple of steps and single analytical path that you want to follow, then it's okay if you don't cache it, right? Because it's going to go and do the evaluation only once, but otherwise it's better to go and cache it. Cool. Next step. So next one is that Spark does provide two different execution method. One is using RDD, another one is using DataFrames. Now RDD with Spark 3.4 and above is kind of like not a lot of people use it, but it does provide a lot of flexibility, and that's why some people go and try to use RDD to kind of take shortcuts, right? That you should not do. And you should use data frames to go and perform your operation. And the reason for this is that Spark data frames are highly tuned for performance using projects like Tungsten and Catalyst. And it also makes sure that you have a good like schema associated with your columns, and as a result it's able to do all sorts of optimization that you would otherwise not be able to get using RDD, right? And lastly, DataFrame also has a very good integration with SQL query. So just in case if you don't want to utilize native Spark functionality and Spark functions, you could always execute SQL query on top of your table, right? If it's easier for you to write a SQL query. So in that case, using DataFrame is going to help you improve the performance, but major of the gain is basically from these two projects called Project Tungsten and Project Catalyst that it utilizes to improve the performance. Okay, so this one is specifically with respect to data frame optimization. And what we want to do is we want to be able to filter the data at read time. So we have covered this before, and I'm covering this again. It's very important that you filter the data towards the source. So as closer as possible to the source, if you filter the data and figure out the right amount of data that you need and just filter that much data, it's going to not only save memory, but it's also going to save significant amount of compute for you going forward, right? So it's very important that you filter the data. I cannot stress this enough. The next thing that you should be doing is that you want to be able to make sure that whenever you do, operations like group by or join or anything, just before that, if you know that you're only going to be using like 2 or 3 columns, just filter it, right? It's better to filter the data before doing complex operation, especially like join, right? If you only need like 2 columns out of like 100 column that you have in your table, as a result of join, then it's better that you filter it so that your network IO is minimized, right? So again, it goes back to filtering only, right? The next one is that you want to ensure that the data skew across partition is limited, right? So what do we mean by this is that when the Spark reads the data, it goes and creates partitions, and these partitions are stored across different computers within the cluster, right? So if your data is not evenly split across all these partitions and across these different clusters, then what's going to happen is that you might end up, overutilizing some machines and underutilizing other machines. You want to make sure that you utilize all the machines equally as much as possible, right? So the way that you could ensure that the data queue is minimum across different partition is by making sure that you often repartition or coalesce the data, and I'm going to talk about repartition versus coalesce pretty soon. But make sure that all the partitions that you create are of equal size, and they're small as well. We're going to talk about it, like how small. If your data is skewed, then again it might could create a bottleneck in your program. And if you find out that your data is skewed, the way that you can do that is simply like, just go and figure out like, go and, check out your the memory footprint using your Spark portal, and then you should be able to see how much each of the stage utilizes the memory and each of the compute utilizes the memory, and based on that you could figure out whether or not the data is skewed. And the way that you could resolve it is by effectively repartitioning or coalescing the data, right? Lastly, use the Spark inbuilt function if there exists one over UDF. So don't try to create your own user-defined function to like, do lead lag type of operation or calculate, some sort of like mathematical operations like averages or weighted averages or moving averages, anything, right? If there is a inbuilt function for Spark, for moving averages, that doesn't exist, but just in case if there was one, then go and try to use it because they're highly optimized over the functions that you're going to write. And lastly, repartition is an expensive operation. If possible, use coalesce. Now, there's if you limitations of using coalesce because coalesce doesn't allow you to partition data more than the number of partition that you already have. So, for example, if you have like 10 partitions, you can't go and say that I want to coalesce this data into like 11 different partitions. You can only coalesce it in less than 10 partitions, or like 9, 8, 7, or whatever, right? So you want to like when you use coalesce, you want to make sure that the number of partition is less than the current number of partitions that you have in your cluster, and it is much more efficient operation compared to repartition because repartition involves shuffling entire data set across different clusters, and coalesce it just it's a little bit more optimized version of repartition. So if you can get by using coalesce, go and try to use coalesce in your job. It's the free partition that's going to speed up the performance significantly as well, right? But yeah, if you don't have any other choice, then in that case repartition is going to be the best bet. And what you'll need to do in that case, I would recommend, is that once you repartition the data, go and try to store each of those partition, like save it somewhere, right? And then you could reread the data, right? So that way you only need to perform repartition once and you don't need to do it like a lot of times, right? Okay, next one is that we can utilize accumulators and broadcast joins. And these are very important because join is a very expensive operation in Spark, and it often involves shuffling around a lot of data across different clusters, which requires network I/O, right? So if you know that one of the data frame is very small compared to the second data frame, like let's say your two data frame, one data frame is like 100 MB or maybe one gig in size, right? And the other data frame is like 5 terabyte. Then instead of doing normal join operation, what you would want to do is you would want to do a broadcast join. So broadcast join would say that the smaller data frame that is hypothetically 100 MB or 1 gigabyte in size, go and make a copy of the data frame across all the clusters that you have, right? So if you sorry, not all the clusters, the computers, right? So if you have like 3 computers in cluster, then it's going to make exact copy of that data frame in each of those 3 machines, and then go and perform a join using that data frame. So that would minimize the network IO significantly, and you could do join immediately. So there's an example of that over here, where you are broadcasting the data frame 2 and pretty much joining it on data frame 1, which would be the larger data frame, right? So you broadcast the smaller data frame. And the second one is using accumulators. Accumulators are similar to kind of like shared variable across different clusters. So if you want to create a global variable across different clusters, then instead of writing like a program like word count program, you could go and just use accumulators and do a count, right? But you do want to make sure that you don't like you don't have too many values that you would want to keep track of. You only want to have like as few values as possible. You just want to make sure that the number of accumulators that you have in your program doesn't go like bazinga. You want to make sure that it's within a reasonable range. But that's going to help you speed up your operation significantly. And accumulators can be used in all sorts of interesting ways. So let's say you're trying to do a prediction on some data, right? On some data frame, and you would want to in that case what you could do is you could use accumulator or broadcast, both, it depends. So let's say a very large model, in that case you could go and use accumulator. But if you're like small model that you want to use to go and make prediction on, then you could just broadcast the model to different computers in your cluster and then go and make prediction, right? So you could use accumulators and broadcast. to your utility in order to improve the performance. By default, I think what happens is that you could enable the broadcast join whenever possible, and Spark would automatically perform a broadcast join whenever possible, right? So by default, I think that configuration is already on, so you don't need to worry about it. Okay, and then we have covered this a little bit last time, which is using the proper file storage technique. And what this goes into is if you know that you're only going to be reading few columns out of the number of columns that you have, then it might be better to store it as a Parquet compared to Avro or CSV. There are also other formats that we covered last time, like SQL Server and whatnot, right? JSON and ORC and other formats, right? Now, especially in the world of analytics, you are going to be in a situation where Parquet is going to be de facto solution for you, because most of the times what happens is that in analytics you get often thousands of column that you would want to store about your analytics that you're trying to capture. But when you're trying to analyze something, you only utilize like handful of column, 10 or 20 or something like that, right? So in that case, Parquet is always de facto winning technique that you'd want to use to store your files. But sometimes if you know that you have less number of rows and you would want to maintain the schema and things like that, Avro might could be beneficial as well, right? So this table pretty much gives you an information about what file storage system to use based on what you want to be able to do. So for example, if you want the data to be human readable, then you would want to use this as the file storage system. By the way, Avros are not human readable, so this is a correction over here, right? So this is actually no, Avros are not human readable. So if you open a file, it's not going to make sense to you like CSV. It's just going to be binary. So it's not human readable, right? And lastly, this is actually at cluster level optimization that we are trying to do. So we covered a little bit of data frame level optimization and the function level optimization and other things. Now we are going at a cluster level and try to optimize it. So a rule of thumb is that sometimes people go and say that because the medium powerful machines are cheaper compared to large powerful machine, what we're going to do is we're going to have a cluster that is formed using medium powerful machine, and we're just going to hire more medium powerful machines. But that could be bottleneck as well, right? Just because there are more machines doesn't mean that you're going to get better performance, because network IO is even higher cost compared to the number of machine that you have, right? So go and choose the large and powerful machine, as few as possible. Even if it costs you a little bit extra, go and try to choose large powerful machines that are few compared to medium sized machine. That would on paper it would look that medium sized machine are economical, but in reality large and powerful few machines are going to be more economical when you consider the network IO, right? So go and try to choose large powerful machine and form your cluster using as few powerful machines as possible, because you would want to minimize the network IO as much as possible, right? And the next thing that you would want to do is you want to make sure that the partition sizes are optimal, right? So the way that you could calculate that is that you would want to have 2 or 3 partition per CPU core. So if you have 10 CPU core, then you would want to ideally divide your data into 30 partition. But there's also a catch over there, that you would want to make sure that your partition, if you have very large data, if you're 30 terabyte of data, then there's no point of dividing it into like 30 partitions, because each of your partition are going to be like 1 terabyte in size, right? And like you would want to make sure that you have more number of partition in that case, and that is very targeted at the garbage collector that Spark has, right? So anything over 1 gigabyte uh, as the size of the partition sometimes causes memory spill. So if you want to avoid the memory spill, and you want to make sure that the memory is fully optimized for the purpose of compute, then in that case it is better to go and have your partition size anywhere between 128 MB to 1 gigabyte, right? So that would actually give you a better performance and better chances at avoiding the memory spill compared to going with the initial rule where 2 to 3 partition per CPU core. Because that actually is optimal in terms of like doing tasks like 2 to 3 partition per CPU core. But on the other hand, if you want to avoid the memory spill, then the optimal size is 1 gig or less, right? So this is like some cluster level optimization, and obviously there are like some more optimization that you could do. But if you do like the optimization that we covered in this video so far, that should actually help you with 80% of your problem, to remove the bottlenecks that you might would have in your Spark job. Cool. Okay, thank you. So that's it for today's video. Please go and subscribe to my channel and please like the video. Thank you.